Hello, my name is David Lafferty and I'm a PhD student at the University of Illinois. Today I'm going to be talking about some of my research on characterizing uncertainties in the crop switching decision problem for US agriculture. This work is carried out in collaboration with my advisor, Dr. Ryan Sriver, and has also received input from many others as part of the program on coupled human and earth systems. We know that climate change poses a risk to the agricultural sector. This figure here is from a recent paper by Ortiz-Bobea et al., who show that climate change has already impacted global agricultural productivity. Specifically, they estimate that agricultural productivity is around 20% lower since 1960 because of anthropogenic climate change. So these risks are expected to continue into the future, and hence there is a critical need to develop robust adaptation strategies to ensure continued productivity gains in agriculture. One possible adaptation strategy is crop reallocation or crop switching, where farmers decide to grow a different crop that may be more suitable for their local climatic conditions. However, the decision to switch crops is highly uncertain and will likely present farmers with conflicting objectives. The existing literature in this area largely neglects these points. Many existing studies rely on integrated assessment models to project land use changes, but these models are quite computationally expensive, and so it can be difficult to probe the relevant uncertainties. Additionally, often only a single decision metric is used, typically in the form of a profit maximization framework, but one can think of other plausible metrics that farmers might care about, for example, minimizing income volatility. So this sets the stage for the science questions of our current research, which are 1. What trade-offs exist for farmers when deciding among major crops? And 2. Which uncertainties are most important for understanding future farm-level income? We use a simple statistical framework to elucidate these potential trade-offs and decompose the relevant uncertainties. We rely on climate and soil moisture simulations from 30 climate models as part of the LOCA statistically downscaled climate product. We use these simulations to drive a Bayesian hierarchical regression model for crop yields, and then couple these simulated yields with future crop prices simulated by a Bayesian vector autoregression. And so in the end, we have a spatially resolved time series of projected income for each individual crop. Our study area is the continental United States, and we choose to analyze 6 major crops, namely maize, soy, spring wheat, cotton, sorghum, and barley. Historical county-level yields are taken from the US Department of Agriculture, and these plots here show on the left the distribution of county-level yields over time, and on the right, the number of years since 1950 that yield records are available for each county. And you see that these 6 crops cover quite a large geographic area, including almost every county in the continental US. We use a Bayesian hierarchical regression model to simulate crop yields. The important predictors here are a county-level intercept, a linear time trend that accounts for technological progress, 2 variables that account for the influence of temperature, and 2 variables that account for the influence of moisture. The temperature variables are taken from Schlenker and Roberts' 2009 paper. They are growing degree days, which are beneficial for yields, and extreme degree days, which are harmful for yields. The thresholds that determine healthy and harmful growing temperatures vary by crop, and this is a major driver in determining which crops are more or less suitable under different climate conditions. For the moisture variables, there is some disagreement in the literature regarding which variables are most appropriate to use here, and so we sample this structural uncertainty by including 3 sets of moisture variables, namely season total precipitation, season average soil moisture, and weekly soil moisture extremes. There are a number of details that I'm skipping over here, but this yield model is based on a very similar model from a recent paper by Rising and Devineni. So if you're interested, I would encourage you to look at that paper, where they also include a comparison to the more commonly used econometric models. To give an idea of the projections from this model, we can look at a single county, Champaign County, Illinois. Historical yields for maize and soy, which are the two major crops in this region, are shown on the bottom left, and then the distribution of projected yields are shown on the right. The three different distributions at each time step correspond to the three sets of moisture variables that I mentioned in the previous slide, and the distributions themselves sample from parametric uncertainty in each yield model, as well as climate uncertainty arising from the 30-member ensemble. And here you can see the importance of sampling from different forms of structural uncertainty in the yield model, where, for example, for soy, cotton, and spring wheat, the third model, which uses seasonal average soil moisture, projects quite different yield outcomes compared to the other two. For the price model, we use a Bayesian vector autoregression. Vector autoregressions are a simple extension to the standard autoregression. So instead of having a single time series that depends on its own lag values, we now have a set of m time series that depend on their own lag values as well as the lag values of all other variables. And this is particularly useful when you have a set of correlated time series, as we do here for crop prices that typically fluctuate together. So the expression for our model is given here. We have 6 crops, so 6 time series, and we choose a lag order of 2, which gives a total of 36 parameters that we calibrate in the Bayesian setting. And so again, just to give a quick idea of what these projections look like, here we show historical crop prices at an annual timescale, inflation adjusted, and then projections out to 2060. The shading in the projections shows the 90th and 99th percent credible intervals, and then the orange line shows just one sample trajectory from a given parameter set. So now we can move on to discuss some results. And it would definitely take too much time to analyze every county for every crop. So instead, I'm going to select 3 counties from different representative growing regions that I hope give some general insight. So we start with Champaign County, Illinois, which we take as representative of the Corn Belt region. And here we see maize and soy, the two major crops in that region, with maize historically delivering a slightly higher income than soy. If we look at projections now, we see that maize and soy continue to be the most profitable crops in this region, at least measured by average income. For the 4 other crops that are currently not grown in Champaign County, cotton looks to deliver the highest income. However, our modeling framework also allows us to test other metrics that farmers may plausibly care about, and one such metric could be minimizing income volatility, here as measured by the standard deviation of incomes over this 20-year time period. And here we see that a trade-off emerges. So while maize and soy return the highest average income, they also exhibit the largest income volatilities. In contrast, the crops that generally result in lower average incomes, like sorghum, spring wheat, and barley, also have the lowest income volatilities. A third metric that farmers might care about is maximizing the worst year's income. So at some point over this 20-year period, either through adverse weather or low prices or a combination of both, farmers will have a bad year, and we would like that year to be as least bad as possible. And so here we see that a decision choice generally aligns with optimizing average income. So the crops that typically deliver the highest average incomes also deliver the highest income during the worst year. And so we can look at some other counties in different growing regions. First of all, we take Custer County, Oklahoma, in the southern US, where predominantly sorghum and cotton are grown, so warmer weather crops. Here we see that maize and cotton look like good options in terms of average income, but again, this trade-off emerges when looking at income volatility, where the crops that deliver the highest incomes also exhibit the largest volatilities. Again, looking at the worst year's income, the crops that perform best on this metric typically align with those that maximize average income. Finally, we look at Ramsey County, North Dakota, in the far north of the country. Historically, this county has had quite a mixture of cold weather crops, almost of equal area for maize, soy, barley, and spring wheat. And again, I won't discuss each of these in detail, but instead just remark that the story is the same here in terms of this distinct trade-off between average incomes and income volatility. Okay, so now moving on to the second science question, which is to understand which uncertainties are the most important in projecting future incomes. To do this, we followed the method outlined in Kim et al. 2019, which decomposes the total spread for a given outcome into different predefined stages. So here we have 3 stages: climate model, yield model, and price model. And the idea is to vary all of the models within a given stage while fixing all of the models after that stage. And by doing so, we acquire an estimate of how much of the spread in a given outcome can be attributed to each chosen stage. So here we focus again on Champaign County, and our income metric is average income over 2030 to 2050. To measure the spread or the uncertainty in outcomes, we choose the standard deviation. And I will say that one caveat here is that this choice is not unique. And so Kim et al. Highlight that there are other measures that could plausibly be used, for example, the range of outcomes or the difference between the 10th and 90th percentiles. And these are equally valid measures and might give somewhat different results. But nonetheless, a couple of things stand out here while looking at the standard deviation as the uncertainty spread. First, we see that uncertainty in the price model generally contributes not a lot to the total uncertainty, but instead the bulk is concentrated in the climate and yield models. And secondly, the relative contribution of uncertainty from climate and yield can vary quite considerably among crops. For example, if we look at maize in the upper left, yield uncertainty is a fairly small portion of the total uncertainty in future incomes. It only contributes about 16% to the total uncertainty. Instead, it's climate which is most important. And this makes sense because Champaign County, as we've said, is in the heart of the Corn Belt. It has historically grown a lot of maize and has good measurements of yield records. And so the main uncertainty here will be what future climate looks like. In contrast, if we look at cotton in the lower right, we see that climate only contributes around 34% of the total uncertainty. And here it is the yield model which is dominant, contributing around 57%. Again, this is somewhat intuitive. No cotton is currently grown in Champaign or really anywhere near Champaign County. So if future farmers were to start growing cotton here, there would be considerable uncertainty about how cotton would respond to the local climate conditions. Finally, we can look at how these uncertainties vary across space. And here I want to focus on the 2 crops that we discussed in the last slide, cotton and maize, and for the 3 counties that we've mentioned before. So here we see that generally speaking, again, price uncertainties are small, and the interplay between yield and climate uncertainties depends on the county, so the location, and therefore the historical crop growing patterns. So these figures confirm much of the intuition from the previous slide. For example, if we look at the middle column for Custer County, Oklahoma, which has historically grown a lot of cotton, the yield uncertainty for cotton in the bottom row is quite small at only 29%. On the other hand, for Ramsey County, North Dakota, which has grown no cotton and is even further away than Champaign in terms of the distance to historical growing region of cotton, we see that the yield uncertainty is huge there at around 72%. So taken together and bringing this back to our science question, which is which uncertainties are the most important to farmers on the ground when making decisions, it really varies by location and therefore historical growing patterns and which crop the farmer might be interested in planting. In conclusion, we've seen that farmers do face trade-offs when deciding among major crops, specifically between maximizing average income and minimizing income volatility. Future work here should address what other decision-relevant metrics and decision levers are truly relevant for farmers. Switching crops is only one possible adaptation channel, and there are many others that might represent a more pertinent decision question. For example, deciding whether or not to invest in irrigation infrastructure. In terms of the uncertainty analysis, we've seen that there are large uncertainties in future income that vary across space and among crops. But we are still likely undersampling relevant uncertainties. So recent work has highlighted the importance of compound heat and moisture extremes in understanding crop yields, and that could be incorporated into our framework here. One additional uncertainty that is likely to be very large is that of future irrigation rates and its effect on local soil moisture conditions and hence yield outcomes. That is an uncertainty that we neglect here, but also could be incorporated. So this work is very much still in progress, and I'm more than happy to answer any questions you might have or discuss this further offline, so please don't hesitate to reach out to me. Thanks.